The modern motion picture brings you romance, education, entertainment. It brings the world's best drama to the smallest town, the poorest man. Behind the glamour of Hollywood lies an industry, turning the wheels which bring these marvels to you. Creative artists and technicians put together the mixture of art and science which makes actors and sets, electricians and lights, cameramen and cameras. There is a roll of motion picture negative film in this camera. The finished picture will be on another roll, known as positive film. These delicate strips of film with their light-sensitive coatings are the materials which record and transmit the creations of Hollywood to the world. This picture is the story of these films and of how the alchemist in Hollywood makes entertainment out of silver. These buildings are some of the movie photo finishers or motion picture laboratories in Hollywood. When you have taken a snapshot of Junior with your own camera, you take your roll of film to the photo finisher and next day see your finished pictures. This is just what happens to movie film from the studio camera.
The photographic process and how it brings a picture to you is explained by this diagram originated by Dr. Mies. When you look at an object in real life, the brain at number 1 receives an image of it through the eye. In photography, the object, the large black X at 2, is imaged by a lens on a light-sensitive film at 3. The exposure period produces a latent image on the film at 4. After developing and fixing, a visible negative image is formed at 5. It is called a negative image because it is white where the original object is black, and vice versa. In order to obtain an image in which the light and dark areas are in the correct relationship, this process must be repeated. The negative is therefore photographed, or printed. Light shines through the negative and falls upon another light-sensitive film at 6, and produces a latent image at 7. Once more, the developing and fixing of the film reveal a permanent image at 8, which is this time a positive image of the original object. Therefore, when this positive image at 9 is illuminated, the brain at 10 again sees an image which is a faithful reproduction of that obtained from the original subject. What happens to the film chemically may be expressed in 3 equations. First, a latent image is formed. Second, it is developed. And finally, made permanent.
The photographic emulsion is made up of millions of tiny crystals of silver bromide suspended in a thin layer of gelatin. This picture shows how the crystals actually look when magnified several thousand times. We want to talk about them for a few minutes in rather technical language because on their peculiar properties is based the whole art of photography. You will note that the triangle is a typical shape in this group, and for simplicity we shall talk about a single triangular crystal. This crystal is made up of a pattern of silver and bromine ions. The silver, denoted by Ag, bear a positive charge, and the bromine, denoted by Br, a negative. The significant detail about this crystal, which makes it of photographic value, is a tiny speck, S, known as the sensitivity speck, consisting primarily of silver sulfide. These specks are probably formed during the manufacture of the emulsion. Let us follow the action when light waves from your favorite movie star pass into the camera to the emulsion. A few light quanta strike this particular crystal, and when a quantum of proper energy hits a bromine ion, it releases an electron from the bromine, leaving it no longer an ion, but an atom with 0 charge. The electron is then free to travel within the crystal, just as if the crystal were an electric conductor. Indeed, we speak of this property of silver bromide crystals as photoconductance, since they conduct electricity when light falls on them. Electrons within the crystal travel freely, and naturally in their wanderings they find the sensitivity speck. Since the molecular pattern of this speck is such that it can trap electrons like a positive pole in the crystal, the electrons released by the action of the light find themselves clustered about the sensitivity speck. The accumulation of these electrons converts the speck to a negative pole capable of attracting positively charged particles. There is at all times within the crystal a movement of ions due to thermal agitation. Under ordinary conditions, the silver and bromine ions move sluggishly about, occupying vacant places within the crystal lattice. In this particular crystal, however, something has happened to disturb the normal state. After being struck by the light, a negative pole was formed at the sensitivity spec, and now positively charged silver ions are attracted to the spec. We follow the silver ions in their slow path toward the spec. Since their movement is due to thermal agitation of the molecules, this action is faster when the crystal is warm than when it is cold, which explains why film is less sensitive in cold weather. The silver ions are gradually drawn to the spec, and as fast as they come within its range, they are neutralized by the electrons clustered about the spec. Eventually, one atom of silver is neutralized at the spec for each quantum of light which hit the crystal, and the sensitivity spec finds itself surrounded by a group of silver atoms. It is the aggregate of these clusters of silver present in the crystals which were struck by light, which are the latent image in the film. This image is called latent because it is quite invisible and of no use to us until a developer reveals it. The latent image is permanent, this crystal pattern being stable at ordinary temperatures. In fact, film exposed by the Andre expedition and abandoned in the Arctic was found 30 years later and developed to give satisfactory pictures. Following the neutralization of the electrons at the spec by the silver ions, the spec regains its original ability to trap electrons, and on immersion in a developer, an ionized molecule of hydroquinone bearing a negative charge is attracted to the spec, or latent image. The secret of the use of certain reducing agents as developers is that their electric potential is of just the right order to be attracted to the specs, but they are not powerful enough to reduce the silver ions in neighboring crystals which have not been exposed to light. One molecule of hydroquinone appears at the spec and loses its negative charge, which is an electron, to the group. Thus, negatively charged, the spec is once more the target for wandering silver ions, and as fast as one silver ion arrives at the spec, neutralizes itself, and leaves the group again positively charged, another molecule of hydroquinone appears and deposits another electron. If this keeps up long enough, all the silver ions within one crystal are reduced to metallic silver, and we have a black deposit forming part of a visible image. The bromide ions move out of the crystal and are released in the developer. To show how a picture of light and dark tones may result from a collection of silver particles, let us see what happens when crystals are given exposures of different intensity. This crystal, receiving much light, has many electrons released and many silver atoms formed. Following development, it is completely reduced to metallic silver. The next crystal, receiving a moderate amount of light, has fewer ions reduced to atoms and has some of the silver and bromine ions left in their places. The third crystal, receiving little light, has few electrons released and few silver atoms formed. Our three crystals then have this appearance. It is necessary to remove these undeveloped silver and bromine ions, and this is accomplished with sodium thiosulfate, which dissolves the silver bromide, leaving the metallic silver atoms behind. The deposit of silver, making up the visible image, actually consists of clusters of these atoms distributed throughout the gelatin layer. These particles are not evident in an actual picture, but may be seen under enormous magnification, as in this photomicrograph.
We have seen how the silver bromide crystals receive and store the latent image, and learned that a developer is needed to reveal it and a fixing bar to make it permanent. In a Hollywood laboratory, thousands of gallons of such developing solutions are in daily use. They are compounded with the utmost care, using purified water and tested chemicals.
But what goes into a developer?
First of all, we need a reducing agent, of which hydroquinone is typical. There are a number of organic reducing agents, such as elan, pyro, glycine, amidol, and hydroquinone, which will convert the latent image to metallic silver. Here we see some hydroquinone added to water and a piece of exposed film agitated in the solution.
But why doesn't it develop?
Well, the reason nothing happens is because the developer will work only in the presence of an alkali. Therefore, we next add some sodium carbonate to the hydroquinone solution. Now observe that development takes place promptly. But also observe that the solution becomes discolored. The discoloration is due to the oxidation of the hydroquinone, and a solution like this would lose strength very rapidly. To prevent this rapid oxidation and loss of developing power, sodium sulfite is included in the formula. To a solution of hydroquinone, we first add some sodium sulfite and then add the sodium carbonate. A piece of exposed film, when immersed in the solution, will rapidly turn black, indicating that the developing power is unimpaired by the sodium sulfite. But now we notice that the solution remains perfectly colorless. Our developing solution is now practically complete. It is desirable, however, to include a small quantity of potassium bromide to restrain the reducing action of the developer so that it will convert only the desired image into metallic silver without affecting the surrounding, unexposed silver bromide. The ability of potassium bromide to retard the action of a developer is illustrated here in an exaggerated way. Both flasks contain complete developing solutions. An excessive amount of potassium bromide has been added to the one on the left. Now we see that the solution with the excess bromide does not develop at all. These, then, are the ingredients of a developer. A, the developing or reducing agent. B, the preservative. C, the alkali or activator. D, the restrainer. In addition to a developer, we need a fixing bath containing sodium thiosulfate to remove the undeveloped silver bromide by converting it to soluble silver thiosulfate. The primary function of the fixing bath, therefore, is to remove the unexposed, undeveloped silver bromide. This action not only makes the film transparent where there is no image, it also makes the image permanent, since the action of light by itself would gradually cause the unremoved silver bromide to darken. In this demonstration, we observe that a piece of undeveloped film becomes transparent when agitated in a strong solution of hypo, because the silver bromide is converted to soluble silver thiosulfate. You will recall that development was carried out in an alkaline solution. It is therefore desirable to make the fixing bath acid in reaction so that development will stop promptly when the film is immersed in it.